Yep. So these packages, you're free to take them and use them anytime. In the future, they'll probably just be sitting here. Templates. So if we click in it and start checking out what the actual code looks like, so here's .c. So what we're looking at is an R package that calls C code using the .c interface. So what we have are two files in the top level directory, description and the namespace, and this is all you need to have a package in R. Description, a namespace, and an R directory that has R code. And then you have an R package, okay? All there is to it. So I have these files on my local computer here, downloaded. And let's check them out from here. So this is just all those same directories. We go into the .c one and check it out. I see my description, my namespace. The README is not necessary. It just gives me something to look at on GitHub. We can cap the description. So this is just a bunch of key value pairs. It says what the name of the package, what it does, demonstrate the use of RC interface. It's got a date and an author. Anyone know who Lucas Jackson is? Yeah. He was the protagonist in Cool Hand Luke, the movie with Paul Newman from like the 70s, which is a really cool movie. Anyway, he wrote this package, gave it to me. Alright, so yeah, just fun stuff. There was that. There's also the namespace. So these are what tells R what symbols to export and make available inside this package. I have a couple C functions and a couple R functions. At export L2 norm means that I have an L2 norm function, or a function called L2 norm inside here. We can go into the R directory and see it. I have this L2 norm.R. Let's check it out. L2 norm. Okay. So here is, so this is the R code that calls the C code. To call the C code, we use this .c interface, and this is one of the possible interfaces to R code. Other ones are .call, .external, .internal, and .primitive. So anytime you're looking through R code and you see one of these, and .fortran is another one if you're calling Fortran code. I have these all listed. But whenever you're looking at the source of R code and you get into one of these, you know that you've hit compiled code somehow. So this is where this R code hits the compiled code. Who has done programming in C? Oh, quite a few people. Okay. So you know that C, the types of the data really matters. You can't just go passing in integers and floating point numbers willy-nilly wherever you want like you can in R and Python. You have to be more specific about it. So here I convert everything into what I want. I want n to be an integer, I want x to be numeric, and I want the output to be numeric. So question for you, why would I do this in the R code rather than the C code? Because I could also make the conversion inside there, but why would I do it here? Yeah? Yes, the error checking and handling is more robust in R than in C. And also, this will work if there's any kind of coercion methods. It can be any kind of object at all, and you can define a numeric method, like to convert something to numeric, and it'll happen. And that's all you need, essentially. So the general principle there is to write as much code as possible inside R before you go into the C code, and just do like the hardcore algorithmic numeric stuff inside the C code. Do all the error checking and other stuff in the R code because it's easier to do there. And it's easier to debug if and when you make mistakes. So that's what's going on. And these comments say everything that is happening. We end up with a list called out, x, and in. So everything that goes in is passed in as a pointer to the C code, and the C code operates on these pointers. So there's also the source code, the source directory inside here. And it has these objects files, star.o, and take them out. And let's look at the actual C code, l2norm.c. Okay, so here, this is C code. We're including the math header so we can get a square root function from C. But now we're actually, so we see a signature that matches what we wrote inside the R function. And it needs to match it positionally and by all these things. We start out with, we initialize our thing to 0. Rather than a vectorized statement, we loop over iterate over every element and add the product of the two elements. So this is kind of the C way of doing things. And you see people that when they first are programming in R or Python, they do things like this and their code is terribly slow because they were taught how to do it in C. But this is how you do it in C, and this is totally fine, acceptable. Okay. So these stars are used for all the pointers, and we're just writing into the actual result output that we want to get our final answer. Any questions on what's going on with these pieces of code? Okay. All right. CD. Okay. So now we're in the top level directory of the package. I have this package. I've written C code. I want to now use it. I could upload it all to CRAN and put it on as a CRAN package, like when we do install.packages, it looks at CRAN and pulls whatever down. But I don't think anyone else wants to see. This doesn't really need to be on CRAN. I'm happy to have it on my local machine. So we can install it from our local machine. So I can do something like this, r command install dot. Okay. Now we see the command was r command install for the directory where we have our package. When we did this, we see this user local op lvm bin clang. So this is an actual compiler. So this r command install is calling the compiler for us and compiling our code for us from the C file into the object files and making everything that we need and then telling us it's done and it's successful. Got all this for. So we don't have to actually write all the compiler flags directly, although we can pass those when we're either in the r command install thing or in our package configuration. We can pass all those flags. So I think it's a little simpler than just writing C code when we have all these things to handle the compilation for us and figure out what to do. But this is also what happens when when you install from CRAN, you can compile it when it comes in. And the same thing happens. It's just using a local file. So now that we've done it, we can access it, or we can use it. So if I open up R over here, it's inside it's a library on my machine that my computer will now know how to find. So I did the .c package. There's also a .call. So R has a couple different C interfaces in the spirit of R. But I can install this one too. Okay, so it didn't do any kind of compilation because make determined that I had already compiled it before, and that's what make does. Yeah.
So the command needs to be all uppercase.
Yep. Has to be all uppercase for this. So this is the other interface to R, which I think is much less pretty because it's not just C code. If it was just C, we could understand it. But this is C written for the R API. So the R programming language C-level application programming interface is what I mean. A mouthful. So if you look at this, you have to know what the sexp means, S expression, from the S language. You have to know what all these things do. But so the code inside turns out to be actually the same as the C code. It's just all the other stuff is kind of different. So there's a lot of technicalities with doing all this. You have to know what the R and the R internal does and how the garbage collector works in protecting things from the garbage collector. Better to avoid this if possible. But it is more efficient than the .c interface because the .c interface copies all of its arguments. So it would seem slower than it really is because it's spending time copying arguments. This does not copy arguments. That's why I'm using it here. Okay. Yeah?
So the double star XP will actually point to the value of X. Is that what it means?
Yep, that's what it means.
So the garbage collector will not collect this point.
I don't have any protect or unprotect statements for the... So that is when I make a new sex object, then that has to be protected from the garbage collector immediately. But I don't really want to get into all the technical details around this stuff. So if you do want to get into the technical details, and I encourage you to do so, there's the Writing R Extensions Manual. So this is like the Bible of how to use all the features that are available inside R. So I'm scrolling down and you can see how my cursor bar is barely moving because there's so much stuff in here. But this is the authoritative manual about how to do all of this stuff. It's got everything in it. And of course, other languages will have their equivalent documentation as well. Okay, so let's use it. We got our dot call. So this is our time for our vector is this. We have our R vector. Our resulting vector is that. Actually, I want to get the elapsed time out of here. TV. Okay. So vectorized. Doing okay. So there's also a package inside R to do this. So we can call the norm function, compute the norm of a matrix, and this is the same thing. So I could call time to do the norm is just call norm of x with type is equal to 2. Tn. Okay, so this norm took how much longer than the vectorized version? Tn over tv? How much longer? Yeah, so 1 order of magnitude. This is 1 order of magnitude difference. So somehow the built-in norm was not as fast as just the simple vectorized thing that we wrote. So if you look into it, you can just look at the actual code for norm. So I print out norm, and it says if the type is identical to 2, then call the SVD function. We look inside the SVD function, and we see it does a bunch of error checking, does a bunch of other things, and then calls another lower level function. And then that keeps going on and calls another lower level function. So it's doing something much more general to handle matrix norms, not the single vector that we're looking at. So it's much more robust. We should probably use it. But if we're just dealing with vectors, we can get a little bit faster by writing our own code. But I have my handwritten C. So here is, this was norm, and written vectorized, built-in norm, and now we do our C version, FV, C, and I think, what is my function called? Dot call L2 norm, okay. L2 norm of X. TC. Okay, so this got down to 10 milliseconds. So that is by writing our own C code, we're able to get quite a bit faster even in the vectorized version. So I didn't do anything special with the C code. I didn't turn on any other optimizations and these sorts of things, but you can always do this and possibly tune your C code even further. So about 10 milliseconds. Let's check that they're all actually the same. All dot equal. That we got the right answer. RV, RN, and RC. Yep, true. They're all the same. So they're all getting the same answer, which is very important. If we're going to write our code faster, it should get the same answer. And this dot call is right here. Okay. So we're down to 10 milliseconds. Okay. Any questions on that? So the idea was if you need to interface to C code, you probably want to be saving all your code inside a package. You can call that, compile that, you can call that with library, and then use it. That's the easiest way. Yeah?
How would you write C code in R?
Write C code directly in R? Okay. So to write C code directly from R, you mean and compile it inside R? Yeah, then you can use RCPP package. That gives you some facilities for that. And also, or inline is another package that has facilities to do that. So then you can just put them right inside and not have to develop a package. And most people prefer the interfaces from RCPP versus the lower level .c and .call interfaces. Those can get pretty technical. So. One thing that's kind of worth checking out. So the if we look at the help options, let's check out the help. R internal function. So the documentation for .internal in R is only true R wizards should even consider using this function. And only R developers can add to the list of internal functions. So this is an example of an interface that's not extensible. This is not meant for the user to come in and write their own thing. But you can come in and write your own .c code or your own .call code, and that's all fine. But .internal is off limits. Okay. Okay, now I'll show you how to do the same thing in Julia. We were doing the norm of a vector, and we got it up to 10 milliseconds to process 10 million elements. That was as fast as we were able to get it writing C code. So let's play around with the Julia language. Not R, Julia. Okay. Over here, I open up Julia. It's a little goofy because my width is so small. But when you're writing these languages, the syntax is really pretty familiar. So I do my same copy and paste, and this is the same code that runs in R will run in Julia. This mathematical code often looks very similar among all these languages. X equals rand in. Okay, we get some big, huge element out. I write a function, L2 norm of X. And now I can write essentially the same as I wrote for the C code. I can write a loop inside Julia for xi in X out plus equals xi times xi. And return the square root of out. End. So I don't actually have to peek in and get the indices of the elements. I can just loop over it kind of the same way I do inside Python. Let's run it. Gives me a generic function with one method. Let's try it. L2 norm of X. Okay, so it gives me some result. We'll time it at time. Okay, so look at the speed, 0.010 seconds, which is 11 milliseconds. So 10 milliseconds is the same as the C code by just writing the for loop inside Julia. Okay, so this is pretty awesome. You can also interface from R to Julia. Rather than writing C code, you could write Julia code, which I think is much easier to write correctly than C code. So consider R Julia if you just need some fast numerical algorithm. So you just pass your object over to Julia and let it run. Okay, so this got it called the 11 milliseconds. Okay, but why did I run this one first? Anyone know why? Warm up the cache. Specifically, yeah, the JIT. So there's something called a JIT, which is a just-in-time compiler, which is how many of these languages work. JIT, just-in-time compilation. So it takes time to compile your code for different types of inputs. In this, we're passing X is the equivalent of a numeric vector in Julia. But this function, I never declared it to be specialized for a numeric vector. Inside C, I did. I said what all my types of everything are. In Julia, I did not. I didn't say anything at all about it. I just waited for it to actually run, and then it looked at the arguments and figured out the right thing to do and compiled the right function for that signature at that time. So that's what a JIT compiler does. It waits until the last possible moment to compile your code. So if I was to time this one, I would be timing how long it takes to compile this function for these signatures and then run it. But when I time it afterwards, I time how long after it's already been compiled. Any questions? So this is core to the Julia language, and it's all built on the LLVM infrastructure, low-level virtual machine, or maybe it doesn't stand for that anymore. I think they changed it. They say it just doesn't stand for anything anymore. So all this compiler technology that's out there. Okay. You can kind of do the same thing in Python, and I'll show it here just for completeness. Exit. Okay. Quit. Everyone else says quit. Julia has exit. All right. So I've written the two functions the same as I did, and if you look at them, they look almost exactly the same as the Julia ones. So if you get all bent out of shape on what language is the best, when they basically look pretty similar at the end. So don't worry too much about it. So here's this Python file. Let us do the same thing that we had. We have n equals 10 to the 7. Open up Python over here. Okay. Get that. Import these things. Make my x mp.random.randin. This is even the same as Julia, which is nice. X.size, make sure it's the right size, this huge object here. So over here I can use some IPython magic if I just want to time it. The command is time it, L2 norm of x. So it's running this function right here, which isn't doing anything special. The difference between this one and this one is just this one has something above the function signature. What's this called? This programming language feature in Python? Decorator. This is called a decorator at JIT. So I have one version that's just L2 norm and one that's L2 norm underscore JIT. The one without the JIT took almost 2 seconds. So 2 seconds from 10 milliseconds. That's a couple orders of magnitude worse because it's running in pure Python. This is like writing a for loop in R. It's also going to be really slow in the same way. We didn't do it, but yeah. So Numba is a library inside Python developed to add this JIT compiler specifically for the numeric type computations that we're doing. So if you have NumPy arrays and you're doing algorithmic numerical stuff on it, developing new algorithms, then this is a really cheap and easy way to get it working. So let's run this and do this same time it, L2 norm of the JITted version. So this time it is actually not timing just one run, it's doing many runs for us. Okay, pretty cool. So we've gotten down to 10 milliseconds again, which is the same speed as C, the same speed as the Julia version and the Numba with the JIT. And it's able to do all this because this function is fairly simple and type safe. So it can infer everything to do and compile all the stuff for us. So it's a trick for getting it really fast and using the speed of a compiled language from just your regular Python that you're using. Any questions on that? I know I'm not covering this stuff really deeply. I would love to have another assignment on actually writing compiled code and write stuff in C, but we do what we can with the time we have, right? So I'm sure you guys aren't begging for another assignment to go along with your project. So feel free to check this stuff out on your own. Okay. So this same idea is possible in R and other languages too, and this is Duncan and Nick are both working on doing this kind of stuff. Python just has a lot more, I think, engineering, basically money that paid developers who have done this essentially. But for R, it's mostly just Duncan and Nick here that have developed some of these ideas for the R language. And it's not robust like this stuff is. They do have some stuff working, so you can't do all this type inference and compile R code down like this. And you should come to Nick's thesis if you want to hear. His thesis defense should be this summer. You can check it all out. Okay. So this was the same thing with the JIT where I had to actually call it, and that's why one of these runs when it did this would have been really slow because that's the one that compiled the code. Okay, that's all I have for compiled languages, so I have a few other things to share with you, final thoughts on the last day of lecture. I want to say thanks for an exciting quarter. It's been a lot of fun. I've learned a lot, this being my first class that I've ever taught. Been very educational for me. I'd be happy if you kept in touch. So write me a note in a year or two, whenever you're doing cool stuff with data. I'd like to hear about it. I'd like to see how you use any of these tools or techniques that we studied in this class. And for that, you can add me as a contact on LinkedIn. I have a link in the lecture notes, and that's how you'll know my contact information. The winning project team, I will be in touch with you by email after spring break. So the projects are due on Friday. Work on them, and Friday the TA and I will grade them, and then probably the next week we have a panel of people from the Data Science Initiative who will look over the top 5 or so and pick out which one they like best. So midway through spring break, we'll send you an email, let you know. I've got some advice for you with computing. All this stuff, it's all good. I mean, I can show you whatever, but the big thing is to be curious and just keep learning on your own. And that's the way to really develop your skills here. I think it's a really exciting time to be in data science and be doing this big data stuff, and the opportunities are certainly out there to apply it all. And so when you want to increase your skills further, then I showed you a few things like the actual documentation, these sorts of really thick, hard to digest books. Read these types of things. It builds character. It'll make you understand what's going on. And once you read them, then read the source code that's underneath them and see how it all works and fits together. That's the great thing about open source software. You can just look into the source code and see if there's bugs, see how it works, see why it does what it does, how it does what it does. And next, after all that, once you read it, then start contributing. I mean, write your own patches and packages and submit like these pull requests. I was hoping we'd get some for this class, like the one that Parul demonstrated, but we didn't get any. So most of the open source people are really friendly, and if you ever want to CC me in the future or ask me how to do some kind of thing like that, I'm happy happy to talk about it. I think it's interesting. Yeah, and treat it like a craft. If it is your field, if this is what you're going to study and do, take pride in it. Take pride in what you do. Make it nice and care about it. All right, that's all I have for the class. I look forward to seeing all your projects on Friday. Have a good spring break. Next Friday. Yeah, we have also office hours today if you want to come to office hours. Yeah, I'll have office hours next week and I'll announce this. Yeah.
Quick question about the peer review.
Mm-hmm.
Are we supposed to use this? Because it seems like it's inactive.
Seems inactive.
Yeah. I originally it was active, and I put full marks on this and saved it and said I would do the rest later. Seems like it's submitted or something.
Yeah, I think you can only submit it once. is the
Once.
problem.
Okay.
Can you add the comment to it? Because it's not so important what the rubric says, but rather what your comments are.